Let's say somebody is driving along the road, and as they are driving, they're going to start from this point. As they are driving their car, they're supposed to follow this path and reach their destination at this point. But as they are driving, we assume that as they start, you start at a lower speed, like 20 kilometers per hour. Then you start accelerating, and this speed will slowly start increasing to, let's say, 30 kilometers per hour, 40 kilometers per hour as you're moving along the straight track. But we all know that as you're moving from this point, when you are approaching the corner, you're supposed to reduce speed, because you cannot go and you cannot negotiate this corner in this constant speed. So it means that as you're approaching the corner, you're going to reduce speed. So if, let's say, you were coming in at around 60 kilometers per hour, when you reach the corner, you're going to reduce to around 20 kilometers per hour. You will negotiate that corner, then you will accelerate again, you increase speed, then you reach the corner again, you're supposed to reduce speed so that you negotiate the corner. Then you will increase speed again to something like, let's say, 60 kilometers per hour. But you, as approaching the corner, you reduce speed to, let's say, 20 kilometers per hour, so that you're able to swerve that corner again, and so forth, until you're able to reach your destination. So what am I trying to say? What I'm trying to say is that if a person is to move from this point to that point, it is impossible in real life for them to be able to use constant speed to move from here, unless the path is completely straight. But in most cases, as we are moving, you will encounter a bicycle along the way, you will encounter a motorist, you will encounter another road user along the road, and these people are going to definitely cause you to have to reduce your speed. So because of these speed variations, we are always unable to move at the constant speed from where we started from to where we ended. So because it is impossible, when we are calculating, we definitely have to find the average speed now, or we'll call it the average velocity. So the average speed will mean that we're supposed to get the total distance covered, and we also get the total time from this point to that point, and when we divide the two, we are able to get the average speed of this person. And definitely, of course, the average speed simply signifies the constant speed this person would have traveled without having to reduce speed and all that. So for us to get the average speed, we simply are going to get the total distance and divide that by the total time, from the point the driver started driving to the point where they ended. It's the same thing. Average velocity is going to be the total displacement in a specified direction between, and divide that by the total time. Now I have to explain. These two, average speed and average velocity, they both have the same SI units. Average speed it will have the same SI units as average velocity. It's all in meters per second or kilometers per hour. Now, what's the difference between average speed and average velocity? Why do these two have the same? Why do they have the same SI units, but if you look at them, they are having different formulas? Now, let me explain some theory here. When we are talking about average speed, speed and velocity, though they have the same SI units, they are different because one is a vector quantity, the other is a scalar quantity. Now, just to take us back to our theory, a vector quantity is a physical quantity that has both magnitude and direction. And a scalar quantity is a quantity that only has magnitude and does not have direction. Now, in this case, velocity is a vector quantity because it has both the magnitude and the direction. But speed is only a scalar quantity because it only has magnitude and no direction. Now, of course, other examples of vector quantities, we have acceleration, we have displacement. Then for speed, of course, for other examples of scalar quantities, we have density, we have pressure, we have mass, and so on. We'll look more into those details when we are dealing with vector and scalar quantities in the physics videos. So because this is a scalar quantity, speed, so we are going to, it will be total distance divided that by total time. Again, distance and displacement have the same SI units. They are both can be measured in meters. But distance, by definition, is simply the space between 2 points. And then the displacement is simply the distance between 2 points in a specified direction. With distance is concerned more on the magnitude. We'll talk about distance to be things like 10 kilometers, 20 kilometers, 30 kilometers. But those 10, 20, 30 kilometers, their direction is not defined. This distance becomes displacement when we define the direction of the distance. So for example, if we talk about things like 10 kilometers in the north direction, now that becomes displacement because it is having both magnitude and direction. If we talk about things like, let's say we are moving 100 kilometers south. So 100 kilometers south becomes the displacement because it has both magnitude and direction. Then so basically it's total distance over total time, also total displacement over total time. It's more of the same. It's just the theory that makes these two stand out to be kind of different. So we'll do an example here to illustrate this. PQR are points along a straight line in that order, where PQ is 40 kilometers and QR is 90 kilometers. A man travels from P to Q and from Q to R at 10 kilometers per hour and 15 kilometers per hour, respectively. Calculate the time taken between P and Q. Now, when we say kph, we shall be meaning kilometers per hour. So now to do this example, we are going to go ahead and do Roman 1, the time taken between P and Q. Now, before we calculate for the time taken between P and Q, we need to summarize the question in a diagrammatic way. These are PQ and R as points along a straight line. So we are going to illustrate those in the diagram. So we have P, Q, and R. Now they're telling us that PQR are points along a straight line where PQ is 40 kilometers. So from P to Q there are 40 kilometers. And then Q to R is 90 kilometers. And also, as this man is traveling from P to Q and then from Q to R, he travels at 10 kilometers per hour. This 10 kilometers per hour is the speed he uses to travel from P to Q. So meaning from P to Q is 10 kilometers per hour. And then from Q to R, and from Q to R, he's going to move at 15 kilometers per hour. So these 15 kilometers per hour are traveled from Q to R. Roman 1, they're asking us to find the time taken between P and Q. Now, the time taken, we know that distance is going to be equal to speed. Distance is equal to speed times time. So now, since they're asking us to find the time, we have the distance, which is 40 kilometers. We have the speed, which is 10 kilometers per hour. So to find the time taken for the object to move from P to Q, we'll make t the subject of the formula. Of course, distance, we denote it by s, is going to be speed, which is v times time. So to make t the subject of the formula becomes t is going to be s over v, which is going to be equal to our distance between P and Q is 40 kilometers. So it's going to be 40 kilometers, divide that by the speed, which is 10 kilometers per hour. So which is divide that by 10 kilometers per hour. Of course, the kilometers will cancel, those that 0 will go with that. You will remain with your answer as 4. This is hour per hour. The hour comes up, it becomes 4 hours. So it means that the time taken to move from P to Q is 4 hours. So Roman 2, they're asking us to find the time taken between Q and R. That's the second part of the motion. We are going to do the same. The time taken between Q and R, still we are going to use this. T is equal to S over V, and we find the time. So T is going to be equal to S over V. The distance between Q and R is 90 kilometers. Divide that by the speed between that, which is 15 kilometers per hour. The kilometers will go by 15 once. By 15 we have 6. So the time taken between Q and R is actually 6 hours. Roman 3, they're asking us to find the average speed between P and Q. Now you realize that as this body was moving from P to R, it was moving at various speeds. When it moved between P and Q, it was moving at 10 kilometers per hour. Then from Q, it increased its speed to 15 kilometers per hour. So it means that for us to find the average speed of this, means that we are going to find the total distance covered, which for PQ, divide that by the total time. That's going to be total distance, divide that by total time. So to find the total distance is adding up the two distances. We know that from P to Q is 40 kilometers, and then from Q to R is 90 kilometers. So it's going to be 40 plus 90. All this distance is in kilometers, divide that by the total time. Now, from our earlier calculations, we know that the total time taken from P to Q, we got 4 hours plus the 6 hours. The 6 hours is the total time that was taken from Q to R. We calculated that earlier. So our answer here is going to be 130 kilometers. Divide that by 10 hours. And so definitely our answer here is going to be 13 kilometers per hour. Kilometers per hour. Now this you can also write it as 13 kilometers per hour, or you write it as 13 kilometers per hour. Either way, it's correct. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia, helping you manifest excellence.